This video shows you how to find the solution to a linear ODE. So note that there are only very few stochastic differential equations out there whose probability density function can be expressed in closed form. All the calculus tricks that are known are rooted in the ODE calculus tricks that have been taught for hundreds of years. Now, by understanding how to solve a linear ODE, you will be part of the lineage and of that very long tradition. So suppose the ODE of interest reads as follows, where the Q and the P functions are deterministic functions of time only. So the solution technique works with the really famous concept of the so-called integrating factor and follows the following cookbook recipe. First, you rewrite the linear ODE in what is called the standard form. Now the standard form reads as follows: dx over dt plus p of t times x equals q of t. Now second, you define the integrating factor mu of t as follows. Third, you pre-multiply the ODE on the left and on the right hand side by the integrating factor mu t. That's what we do in the next line. You have mu t dx dt plus p of t times mu t xt equals mu t times qt. Now note, independent of what the mu t looks like for that linear ODE, the left hand side takes the following expression due to the product rule, meaning pause the video to really ensure you see the following equivalence, that you can rewrite the left hand side as the change of the product x of t times mu t with regard to dt. And the right hand side stays as it is. Now we bring dt to the other side. So now we have d of xt mu t equals mu t qt times dt. And now the fourth step, we integrate both sides separately. Meaning for the left, we integrate the imaginary 1, the constant 1, with regard to dxu mu u, and the right hand side is integrated with regard up to time. So integrating the left hand side gives you xt times mu t plus k1, that's the integrating constant, and the right hand side we leave unspecified for the moment, as we haven't specified what the mu and the q look like. We just know these are only functions of time. And now you solve for xt, bringing mu t minus 1 and the integrating constant k to the other side. And in step 5, you would try to find an explicit solution to xt, meaning you would now have to solve that remaining integral. Now let's look at one example. Suppose the ODE of interest reads as follows: 2 times dx over dt equals 4x plus e to the 2 times t. Now the good thing about a recipe is that you can just follow it. The more practice you get, the more you can freestyle. But for now, let's just follow the recipe step by step. So step 1, rewrite the ODE in its standard form. That means you write it as standard form dx dt plus p of tx equals q of t, and you see that the p of t for our application equals minus 2, and the q of t in the application coincides with 1/2 times e to the power 2t. Now in step number 2, you define the integrating factor, mu of t, which is the exponential of the integral of p of SDEs. Now the p of t is a constant, minus 2, so the integrating factor takes that nice shape of e to the minus 2 times t. Now third, you pre-multiply the ODE by the integrating factor, and already you realize that the left-hand side can be rewritten more compactly due to product rule as follows. The change of xt times e to the minus 2t with regard to time needs to equal 1/2. Now you integrate both sides and we use that t0 equals 0. So the left integral will simply be the integral of d xt e to the minus 2t, and the right integral is half du integrated up to t. So the integral of the left hand side is then simply xt times e to the minus 2t plus an integrating constant. On the right hand side, the integral will be half times t plus also an integrating constant. I merge both integrating constants into the k. Now in the fifth step, we try to find an explicit solution for xt. Now in that example, that isn't too difficult. We can rewrite xt as being e to the 2t times the sum of k plus 1/2 times t, where k can be any real number. Now notice, if there was an initial value given for x0, the previous family of solutions, because k can be any real constant, would then boil down to one unique solution, namely e to the 2t times 1/2 times t plus the initial value x0.